I thought we should consider another example of buoyancy. In this case, we have an object which is more dense than water, so it's not going to float to the top of the container. So this is very similar to the previous example. And in this case, we have a rock that has a mass of 2.5 kilograms. It has the same volume as the block of wood, 425 centimeters cubed. And the question says, assume the rock is suspended by a string in the container of water. The first question asks, what is the weight of the rock? And so we know that weight is just equal to the mass of the object times gravity. The mass of the object is 2.5 kilograms. And we assume that gravity is 10 meters per second squared, so that gives us 25 newtons. So we have two objects that have exactly the same volume, but one has a greater weight than the other because it's more dense. The next question asks, what volume of water is displaced by the rock when it's totally submerged? Whenever an object is totally submerged, it's going to displace the same amount of fluid as the volume of the object itself. So in this case, the volume of the water that's displaced is exactly equal to the volume of the rock. And this is always the case if the object is completely submerged. So this is just 425 centimeters cubed. The next question says that what is the mass of the water that's displaced by the rock when it's totally submerged? So the mass of the water we can find in the same way that we did previously. We can use the fact that we know the density of water, and density is equal to the mass divided by the volume. And so we know the density of water is 1 gram per centimeter cubed. And that's equal to the mass of the water displaced divided by the volume of the water that's displaced. And we know that 425 centimeters cubed of water is displaced. So if I want to solve for the mass, I have to multiply both sides by 425. Whoops. Centimeters cubed on both sides of the equation. Centimeters cubed cancels, 425 cancels, and I know that the mass of the water is going to equal 425 grams. So there's a lot less water mass displaced in this versus the mass of the rock itself, and that's because the water is less dense. So the next question says, what is the weight of the water that's displaced? And so just like the previous example, we know that weight is mass times gravity. The mass has to be in units of kilograms, so if we take 425 grams and we divide it by 1,000, it gives us 0.425 kilograms. And so I can calculate the weight, 0.425 kilograms times gravity, we are assuming is 10 meters per second squared, so that gives me 4.25 newtons. So this is very similar to the previous example. The next question says, how much buoyant force does the surrounding water exert on the rock when it is totally submerged? So we know the following. If I draw in my picture, I know that the rock itself, has a certain weight, right? And the weight of the rock is 25 newtons. And we know that the buoyant force, according to Archimedes' principle, is exactly equal to the weight of the water displaced. And we found in the previous problem, the previous part of this problem, that the weight of the water displaced is 4.25 newtons. So there is a upward buoyant force equal to 4.25 newtons. And of course there's also some tension in this string right here, which we could figure out the tension in that string, because the tension, if this is in equilibrium right now, would have to exactly equal the weight of the rock subtracting off the buoyant force. Okay, let's come over here. If the rock is released, what will be the net force acting on the rock? So this is sort of answering the above question to some extent. So if we were to cut the string, we were to look at the forces acting on it, we would have the weight of the rock acting down, which is 25 newtons, and then acting up we would have a little tiny buoyant force of 4.25 newtons. And so once the string is cut, there's no longer any tension, and so the question is, what is the net force acting on the rock? And so we have a downward force of 25 newtons, so the negative sign is indicating that it's in the downward direction, and then we have an upward force of 4.25 newtons, which tells us that the net force when it is cut acting on the rock would be negative, let's see if I can get this right, 20.75 newtons. So the net force is acting downward once the string is cut, which means that the rock is going to sink to the bottom. Eventually the rock gets to the bottom, and part G says, when the rock eventually reaches equilibrium again, after being released, the buoyant force on the block is now, okay, so the rock is now sitting on the bottom. And we want to know what the buoyant force is that's acting on it. So we can ask ourselves this question: what is the volume of the water that is displaced? And so in this case, the rock is still displacing the same amount of water. The same volume of water. If that's the case, that means that the weight of the water displaced is the same. So the same weight of water. And since the buoyancy force is equal to the weight of the water displaced, the buoyancy force has not changed. So 4.25 newtons is going to be equal to the buoyant force. So when an object is totally submerged in a fluid, the buoyancy force is going to stay the same no matter where it's located in the fluid. But if an object moves out of the fluid, like if it floats to the top, like in the previous example, then the buoyancy force will be reduced because some of the object is actually then above the water and it's not displacing as much fluid. So the more fluid you displace, the larger the buoyancy force is. In this case, the buoyancy force doesn't change because the object is always completely submerged because it's more dense.